Hello again everybody, and welcome to the first Fluids video. I'm going to try a slightly different format. I've pre-recorded most of the simulation and I'm just going to narrate while I play it back for you. So let's get started. I'm going to start by going to Workbench. And what I'm doing there is just checking to see them recording. Haven't done this in a while, so. Alright, you'll go to Fluid Flow CFX, drag that into the box. Double click to go to Design Modeler. While you're waiting for that to open, we're going to, well, I'll tell you what we're going to do. We are going to make a pipe with a heated wire in the middle of it. So air will be flowing through this pipe, and we're going to find out a few things. We're going to find out the temperature distribution throughout the pipe as a result of that heated wire. We're going to find radial velocity because of that heating. Actually, never mind about the radial velocity, but we will plot velocity as a function of length. Well, more accurately, position, not length. So we're going to plot velocity as a function of length. And as you can see, what I'm doing here is making a circle. Two circles. I'm going to go back a little bit so you guys can see this again. So I made two circles. I dimensioned them to be 0.5 centimeters. The inner one to be 0.5 centimeters and the outer one to be 6 centimeters. And what I'm doing now is zooming in, and you can click the move command, then click on the dimensions to move them to a better place where they're more visible, because it's kind of disturbing if you have many dimensions. Alright, now go to extrude it by 120 centimeters, which is what I've done there. And now you're done with Design Modeler. That's all the geometry we'll need. Next, go to meshing. This is the most complicated part and the most important for a fluid simulation, because fluids need better meshes than solids to get a more accurate conclusion. Now we're just going to try generating the default mesh. Update or generate mesh will work for this. Now zoom in on a face, see what it looks like. Notice all of the, circularly weirdness that's happening. It should not be like that. It should just be nice, neat layers going all the way down. So we're going to fix that by doing a face meshing, not a face sizing, a face meshing. Actually, I think I do an inflation, not an inflation layer, but a sweep method first. Yep, insert method. Okay, so what a sweep method does is it takes what's on a face and it sweeps it all the way through. So every single layer of elements here will have the same kind of mesh. Every single plane throughout that bar. So go insert method, click apply for the body. Now go to automatic, change it to sweep. I'm going to go back a little bit and narrate over what I'm doing here because I'm doing it kind of fast. So insert method, geometry, click the body, apply. Go to automatic, sweep. Now you'll get a bunch of selections here. Now it wants to do it automatically, but sometimes it won't be able to guess what you want to do with this sweep method. So you're going to click the automatic box, click the drop down menu and change it to manual, source, and target. Now you see a source and target selection boxes appear below that. And these are faces, because you can sweep a face through a body. You can sweep a 2D object through a 3D one. So for the source face, you're going to click this face. And with the target face, you're going to rotate around and click the other face. Now, you'll go to the number of divisions, under sweep numDisk, it's currently set to default. You want to click that and set it to 200 was what I found after some trial and error. There's a 512,000 node limit, and I'm going to specify the mesh accordingly. Now we're still not done. That face still looks pretty nasty. Actually, I don't think I updated it after this, but we'll see. So we're going to do that face meshing. It doesn't matter which face because the sweep method will sweep it all the way through. Now just to recap what I did there. So you click a face, don't suppress it, map the mesh, yes. And quadrilaterals are fine because four-sided elements will give you pretty nice results for a lesser element count. And we're all about economizing in the mesh section, because I don't think you guys are limited, but I am limited by 512,000 nodes. So I'll be sticking to that amount for every everything that I do. Specify 100 internal divisions and then update the mesh again. I like to zoom in on a face while I wait. There we go. See, now look at this. It's nice and uniform from the heated wire in the center to the circumference there. You know, you might ask, why are we doing this geometry if we're having a wire in the center? Don't we want to model the wire? We can insert another body there and do a domain, but we can model a heated wire by having that surface do certain things. And what we're modeling is the fluid region. So this face on the exterior is the boundary of the pipe, and this face is the boundary of the heated wire. Because the pipe and the wire itself are not fluid, we don't need to model them. We can just do the appropriate boundary conditions. If we were doing some sort of interactions between fluid, like if we were having a fan here, obviously fans are solid, we'd want to model that fan and then specify it as another domain. But we're not going to do that yet. Now I'm just zooming in. Look at statistics. I'm under the node limit, but I still want some more. So I think what I do next is edit some of the sizings. Also, if you want to figure out how big your elements are, you can drag to try to line them up with this ruler. I changed that to centimeters. If you didn't do your geometry in centimeters, you should go back and do that now. I'm doing the same thing, measuring the size of these. This is about the best I can get for this for these dimensions, because I'm starting to brush up against that 512,000 node limit. Now updating the sweep method to give me some more resolution in the longitudinal direction. I think this takes a while. Alright, the meshing's done. Notice I'm over, so I go back and lower the node count, or lower the division count. Usually it tries to highlight the volumes that it's meshing and the faces that it's meshing, but that's only if you've done something super complicated on a face. So I was at 535,000 there, so I'm still over. So I'm going from 220 to 210. In future videos we'll do more complicated geometry, so we'll spend more time on the geometry step and the meshing step. So there we are. We are 536 nodes under 512,000. So once you're done with that, you can obviously close out a mesh and then double click the launch setup. This is by far the most important part. There we go. I think I spend most of my time in this. There we go. I think Bandicam was dropping some frames there, but you shouldn't care about that, because you don't need to see the window opening, just when it's open. This is what it'll look like, the setup step. It's different than the static structural, notably that everything's in little folders here, and there aren't any labeled buttons. But you can, but if you follow my directions, you should be fine. First thing you want to do in setup is, well, inspect your geometry. And then, I don't know if you saw this, but the first thing you want to do is check the analysis type. You want to go down the list. So analysis type, we don't care about multi-field coupling yet, but those are the options. Steady state or transient are the main options. So steady state is what a system will, or what a fluid or thermal system like this will be doing when it's how do I explain this? When you've been doing something for a long time. So let's say you have water in here and you're pumping water in, or it's being drawn by a fan at, let's call this the outlet. So let's say you're drawing water in. Now, if that heated wire has just started heating up, there'll be a definite change in the water temperature for time, but eventually it'll even out and the heat will flow steadily from the wire to the water, and there'll be some even temperature distribution. It'll all settle down. That's what steady state means. If you're doing something unsteady, you'd want to do transient, and then you have to specify some time steps and other things. Right now we'll do steady state. Next thing you want to check is your domain. So I just clicked on default domain there, and by default the domain is just everything. So under default domain, this is where you specify what your fluid is. Don't bother with any of these, but your material library and air at 25 degrees Celsius is what we want. Now, under fluid models, actually I'll go back to recap some of the things I didn't voice over. Material library, air at 25 degrees Celsius is what you want. Now, reference pressure is very important. It is the reference pressure to which all your relative pressures are added to. So a relative pressure of 0 atmospheres will mean a pressure of 1 atmosphere. This is subtracted from all of the other pressures. So the difference between absolute pressure and gauge pressure is another way to put it. We don't care about any of these options, so next thing to do is go to fluid models. And those are the options for fluids. We want continuous fluid. Reference pressure, very important. Go to fluid models. Now, because we're having a heated wire, we don't want isothermal. That means there's no heat transfer and everything's at the same temperature. So go to thermal energy and click that. Now, for turbulence, there are several different options. Shear stress transport is a solving method that will allow the solver to determine for itself whether flow is laminar or turbulent. Turbulent means there's a whole bunch of changes in velocity and weird ripples and stuff happens. That's a good enough explanation for what we're doing. If anyone has questions, I can definitely address those. Wall function, there's only one option, we don't care. There are options for combustion and thermal radiation there as well, but we don't care about those right now. Now, initialization is very important because it is I'm recording this at like 6 a.m. and I just got out of bed, so I'm a little tired. Alright, domain initialization. Initialization is very important because it gives the equations somewhere to start besides all the boundary conditions you specify. Say if you Actually, I can't think of an example right now. I'll probably think of one later. But it's very important to initialize your domain to provide some base that the equations can use. Provide some basis for the equations to solve. Alright, so for this simulation we're going to have an outlet velocity of I think 10 meters per second. So that's what I'm specifying. And at steady state the fluid will already be flowing through here at 10 meters a second. So we want to initialize all our fluid to 10 meters a second. So the way you do that is automatic with value under Cartesian velocity components. You want to check which direction the flow will be flowing through. In this case it's the negative z, so 0u, 0v, and negative 10 w. uv and w correspond to velocities in x, y, and z directions respectively. Low intensity for turbulence, I'll probably explain this in class. Well, not class, our meetings. Quick OK to close out of that. Now next thing you want to do is you notice this default domain default checked. I think I go into that just to show you what it is. Now it's applied to all, sorry, I'll pause. Now it's applied to all of these faces because we're in default domain default. Everything is highlighted and it says it's a wall. That's not good because it assumes that this is a wall, that's a wall, that's a wall, everything's a wall. So nothing will be happening to the fluid in there, it's constrained. So we want to insert some boundaries. There we go, highlighting the wall. Now click OK. Now go to default domain. This is the button that you want to click. It's insert boundary. Now the first boundary that we'll insert is an outlet. So type in outlet and then hit enter or click OK, and it recognizes the name of that boundary, so it'll automatically think it's an outlet. That saves having to specify this. Now go to the I believe I go to this side. Yes. Now make sure you've clicked on this location box before you highlight the face. Now clicking apply will attempt to make that change or attempt to establish this boundary condition, but it'll give you a warning because you haven't specified enough conditions. So click OK there. Now go to boundary details. This is where we specify the boundary conditions that the equations need to be solved. I believe I do Cartesian velocity components after switching from this, and I realized that not a great thing. Because normal speed, normal speed means it's in some direction normal to this face, so on the z or negative z directions. But to specify fully the velocity, I use Cartesian velocity components because I'm not sure if the normal speed is in the z or negative z directions, and having fluid going into an outlet is not bad. The solver does not like that. Don't worry about any of the other options. I think I also used relative pressure, but I'm not completely sure. No, I didn't. So just do that, click apply, then you're done with this boundary condition. Alright, we still want more boundary conditions, so we're going to insert another one. We're going to name it the outer wall. It doesn't recognize the name, so we have to specify it as a wall. We're going to select the outer face after clicking that box, of course. Now the boundary details. No slip wall is a good enough assumption for this. Heat transfer, or a smooth wall, first of all. We'll do smooth wall. Roughness kind of mucks up the simulation. It'll make it run for longer because some of the equations won't converge as fast. But so we'll ignore that for now. We'll think it's a nice smooth wall. Now heat transfer. Adiabatic means there's no heat transfer, which is a terrible assumption to make for a pipe with heated air flowing through it. So we're going to specify what the we're going to specify some kind of heat transfer to the outside of the pipe. We're going to do that with a heat transfer coefficient and an outside temperature. Now, the heat transfer coefficient, I think I used temperature at first, but then switched the heat transfer coefficient. So we'll wait on that. You can go ahead and do temperature first, but I think I do heat transfer coefficient at the end of the day. It's temperature 20. It doesn't matter which units as long as you're consistent. Actually, no. It was precisely the opposite of that. It doesn't matter which units, and you don't need to be consistent because the software will convert automatically for you. So 60 degrees Fahrenheit for the outside temperature. Now, I'm going to insert another boundary condition. No, I think this is where I go back and do heat transfer coefficient. Yep, there it is. So the heat transfer coefficient, if you've taken a thermal sciences class, helps quantify the amount of heat going out of this wall. And heat transfer is driven by a temperature gradient, so it needs you to specify the temperature. In the heat transfer equation, it will use the temperature of the fluid near that boundary to determine the gradient. So the temperature of the fluid with regards to the outside temperature is what matters, and that coefficient. Typical convective heat transfer coefficients range anywhere from 5 to 100, maybe even thousands of watts per meter squared Kelvin. 40 is kind of typical for air flowing over that pipe. And besides, this isn't actual problem solving for the rocket team or for a class, so I'm just using 40. It's a nice example amount. Now we're going to do another boundary condition. Heated wall. This will be the interior. This will be the wire. Actually, not heated wall, heated wire, excuse me. So it's another wall. You can box zoom. So you right click and drag to box zoom, and it'll snap to whatever box you drew. So now I'm assuming you click that, click the inside. Now this one will also be heated. And we're going to specify a certain heat flux. So if you use conservation of energy, there will be a certain amount of power being dissipated by this wire. And you can calculate that in advance. You know, P equals IV equals I squared R, if you've done physics 2, which I believe you all have. Now heat flux in. This means into the fluid. So I think I do 60, and then I change it to 200. Now we're going to do, we still have another boundary condition to specify, because where the fluid would be coming in, it's still a wall. So because there's a fan, a simulated fan at the outlet with a certain velocity, if we were to specify an inlet with the same velocity, that wouldn't be, that'd be like another fan with the other fan. So what we're going to let the software do is we're going to let it solve for the inlet velocity by itself. And the best way to do that is an opening. And this is the only boundary condition that will let you do that. It's a very weak boundary condition. So we're going to click that where the inlet would be. Now in the opening options you get mass and momentum, flow direction. You could specify it as normal for now. If you have, say, if you're going to model some air being drawn into this from a wider domain, then you wouldn't want that to be normal because there will be weird stuff happening. But for now, we're just modeling this part. It's normal, it's fine. We're going to specify the opening temperature. I think I specified it as the same temperature as the fluid. Yeah, 20. this simulation won't make the most physical sense, but it's still quite reasonable. I'm mainly doing this just to show you guys how the setup and meshing steps work and how the solution works, because there are things you can do while it's solving. I'm pretty sure I leave this alone. So the Cartesian components are just the direction you're specifying. I think I just use normal. Nope, I'm doing this. So -1 means the flow will be flowing entirely in the z direction. This is an okay assumption to make. If I said normal, then this would allow fluid to flow out of here as well, which would not be happening if there was a fan at the other end, which is what we're simulating. Now that that's done, I think I'm double checking the temperature. Yeah, I changed that to 20 degrees for the outer wall. So there will be fluid at a 20-degree temperature. There's an outer wall at 20 degrees, and the heat of the wire is heating everything up as it comes in. Double checking all of my boundary conditions, making sure they're okay. That's where I change it to 200. If you notice, I'm recording this at like 10:40 at night. That was last night, fun fact. Now I don't know what I was doing there. Nice to double check the basic settings and fluid models, thermal energy, so it's just transport, no combustion, no radiation. You can also include electromagnetics for the fun of it. Don't say actually do that, just and then double check the analysis type. Now double check initialization because it will have been added in. Now the final step of setup is to go to solver control. This is where you control the solution process, and you're basically telling the solution when it's reached a good enough model. I'll explain more later. But now the iterations under convergence control, this tells the computer how long or how many times to attempt to solve the solution and improve upon a previous solution. So what it does is solves a bunch of equations using numerical estimates, guesses for lack of a better word, and then it has some kind of residual value that's left over from guessing from all the equations, and it uses the residual value, and the values that it solves for, it plugs them back in to all the other nodes and solves for a set number of times. So it's usually better to specify a large number for this, probably like 1,000. Now the length time scale, even though this is a steady state problem, it has to attack this as if it were transient, because the solutions that it's solving cannot be solved explicitly. You have to numerically iterate through like this, and it can only do that over certain time steps, and this is called false time. Now for the scale of the time steps, the scale controls how fast this will converge. But if you set it for too small, it'll try to go too fast, and if your boundary conditions and your mesh aren't good enough, the residual values, everything left over when solving those equations, will blow up and it'll diverge and you'll get nothing. So best thing here is to use aggressive for the length scale. Leave the time scale factor unchanged if your solution isn't converging fast enough in the solver. While it's actually solving, you can change this and it will most likely converge faster. But of course that's limited by your mesh and your boundary conditions. Now the convergence criteria is one of the most important parts. So the residuals are everything that's left over when it's done guessing at the solutions for those equations. And I'll show you those later. I'll show you the equations later, but the residual target right now is 0.0001. That's too high. So So we usually want to set that at 10 times 10 to the negative 6. So 1e negative 6 will work. There's a difference between root mean square and the max amount. Go with root mean square. Conservation target, I kind of forget what that means, but I'll explain it to you guys probably in a future video. It's nice to have a value of 1 e to the negative 4th. 10 to the negative 4th, so 0.0001. Now that you're done with that, don't muck around with anything in here unless I tell you to in a later video. There's some advanced options, expert parameters, like you can tell the software what equations to solve. That's an example. Now, nothing else, take a look at your domain again. Now X out of this. The last part of this is solution. And the solution is the actual solving process. So you'll get a window, double click on solution, you'll get a window, it says starting CFX solver manager. Now this is the now the define run is where you set up the actual kind of solution process hardware wise. So this tells the parallel environment here thing is you can partition the mesh. Remember, I'm at 511,464 nodes. You can split that up so that cores on your computer can run a certain amount of that at a time. So you can split it up into about 60,000 nodes per logical processor is what I'm going to do here. So to do that, you switch to Intel MPI local parallel. I have a quad core processor, so I have 8 logical cores, or 8 logical threads. So you can partition the mesh into 8 sections. So this will allow it to solve faster. Now, on the computers in Color 1254, those are 12 core processors. So I believe you should do at least 12 partitions. 12 should be sufficient if you have about 512,000 nodes like I do. You guys can probably do more, but that checks out a different kind of license. And if too many people are doing more than 512,000 nodes at once, it will kick some of those people out of the solution process. It only asks for the license once you actually go to solve. Now, that's pretty much it. I think I scrolled through some of the other things too. You don't want to do initial value specialization unless I tell you to in a later video. This is the detail of the partitions. That memory allocation factor, sometimes if you don't have a good enough, if your computer uses up too much RAM while trying to solve these equations, it might be useful to increase this a little bit, but I'm going to leave it. So I go back to the partitioning page, run definition. So it's useful to have around somewhere in the tens of thousands of nodes range for your per partition. If you have any less than that, it'll probably run slower because it'll try to integrate all the partitions at the end of each time step. Now once you're done with that, click Start Run. Now you'll get an out file here. This is where it just lists everything that it's doing. So this is all the information at the start of the run, tells you the solver, tells you the license, tells you the amount of nodes, gives you a notice for the heat transfer coefficient, gives you some statistics on the mesh, 511,464 nodes, total number of faces, total number of other things. It tells you the equations that it's solving. So X, Y, and Z momentum and conservation of and the continuity equation for you fluids buffs out there. It'll solve the thermal energy equation and the turbulence equations as well. So the convergence history is where it really starts. Through each loop iteration, that is where it starts solving the equations. It solves wall scale first, then it'll solve the momentum and the continuity. It'll solve the heat transfer, then it'll solve the turbulence. It runs a lot faster than this usually, but the reason it's not running as fast is because I'm recording, and recording takes up a lot of CPU. So with 8 partitions, each taking up, what I'm actually doing right now is highlighting, it checks for isolated fluid regions. So let's say if you've set up a fluid model with the rocket CAD, if you forget to specify the inside as, I think we might have to specify it as a solid when we do that, because if you don't have the inside of the rocket open, it'll say it's an isolated fluid region, and if it finds any isolated fluid regions, it'll just quit. It'll have a hissy fit and it'll quit on you, because the equations don't work for isolated fluid regions. I mean, you don't need the equations for isolated fluid regions because nothing's moving. So yeah, I'm going over what I've just told you. Speed this up a little bit. So once it's got to, give me a second here. Forget that. This will graph those residuals per time. Well, with the false time step down there. So that's 1, 0.1, 0.01, 0.01, 0.0001, and then 1. This is the convergence target. So ideally, we'd want these lines to go below this eventually, and that is what happens because I specified the mesh well enough, and I've specified my boundary conditions. So I'm going to skip ahead a little more. Again, this is running so slowly. Here I'm just showing you the equations that get solved. Some of these encompass like 20 terms, and it's nasty. So all of these bars indicate average velocities. U is an average velocity. F, I believe, is an average body force. P, I'm not sure what that is. That is a stress field. So yeah, all the averages are because of turbulence. See, they're used to describe turbulent flow. So in turbulence, you have to use an average velocity when solving these equations. Otherwise, you have to break the fluid domain up into many small elements, like one for each atom, probably, and take the Lagrangian approach of solving those things. Because each particle will have a certain velocity, but we care about an average velocity to make things easy enough. We don't care about the derivation. I will skip ahead again. Here we go. If your simulation is not converging fast enough, what you can do is go to Tools, Edit, Run in Progress. If you're doing a super important simulation, then you'll want to write a backup file. But I'm not doing one, so I'll click No. Drag that over there. Go to Flow Analysis. Go to Output Control. No, Solver Control. Excuse me. Go to the first convergence criterion, and this is where you can edit that timescale factor. And this will run the time step faster and allow these to converge more quickly. Beware if you set that too high. Remember I said in setup that's limited by your mesh and your boundary conditions. If you set that too high, these will blow up upwards and diverge. So it's nice to go like 3, 5, probably the maximum that you want to take that is 7 or 8. Notice it's not going to run any faster because I'm recording. I'm going to switch to a different video, and I think that's where I've already, Yeah, what I did last night is I stopped recording, allowed the run to finish. It took like 10 minutes after I stopped recording. It would probably take several hours, if not more, if I continued recording while doing this. So y'all can just leave your computer screens. I was kind of messing around. If you want that to actually change, you want to save and then exit. And once it reaches a certain time step, it will write in that new timescale factor and continue solving that way. I think I wait for that to happen. Give me a second here. Yep, here we go. Reading modified command file differences are given below. Timescale factor, it shows you what it was and shows you what it is now. And then gives you more timescale information, which these, I believe that was tripled. Then it continues solving. So I'm going to go to another video. I believe this is where the equations finally converged. Yep, so this is the heat transfer. This was about where I started. This is where I modified the time scale, so it allowed everything to solve faster. And heat transfer usually bottoms out somewhere depending on how good your boundary conditions are. So that's fine. If everything goes below your convergence target, 1e⁻⁶, the simulation will automatically terminate. It'll finish for you. There I'm highlighting in the the momentum and continuity equations where the time scale was changed. So notice everything has gone below 1e⁻⁶, and heat transfers bottom out, so I decided to stop the run after 89 coefficient iterations. And stopping the run will enable you to get results. It will update the results box, which is the final box that we care about. And we're now going to go to that results box. So I believe I saved. Yep, video 6 is where I saved it. Okay. Hey, 42 minutes. I've been going for a while. I'm going to wait for that to load. This will have the there we go. So if you quit the solution before it's all reached all its convergence criterion yet, you know, remember 1e⁻⁶, it'll show a check mark, but pause. That's fine as long as it's sufficiently converged to your liking. You can click on results and it'll show results. Now you'll get a box somewhat like this. It looks kind of like setup, except you have a bunch of fancy, that one's a vector field, contours, streamlines. You can draw some things, you can track particles, you can render a volume, and you can do some animations. I'm running kind of short on time right now, so I'm not going to do any animations, but I will show you how to do some basic things. Let's say we want to plot temperature along the radius of the pipe. To do that, we need to have a plane for it to draw that contour graph on. So plane, you could say plane 1, I don't really care. The ZX plane goes along that pipe, or you could do the XZ or the YZ. Doesn't matter to me. I'll do YZ. It'll be different. Okay, now we don't need to color the plane or anything. Actually, we could if we want to, but that's a different type of graph that I don't want. That is less nice. We're going to apply. As you can see, our plane got highlighted in there. If you uncheck all the other boxes, see, there's the plane. Now, if you want to color that plane, say with a contour, you can insert a contour. Let's say, let's do 12 or 13, let's do 13 contours. You can, all domains, remember we have one fluid domain, and we do plane 1 as the location. Let's do temperature. Now if we do global values, it'll do that in Kelvin, and notice, remember, this is the opening, the inlet. That's the outlet. So fluid's flowing this way and it's getting heated up by that wire, because that wire has a certain heat flux. Now notice, and this is what would happen in real life as well, just from fluids and heat transfer experience, everything starts to heat up very nicely closer to the wall. It's about 10 degrees Celsius more at the wall than it is elsewhere. So I'm zooming out right now, and I can drag it along to see this sort of thermal boundary layer start to form. And notice the blue and the light blue especially are getting more pronounced, and the red is also more intense as well. And this narrowing at the end, that's a mesh related issue. We don't care about that. If you see something that doesn't really conform to your understanding of the physical laws, it's probably a mesh issue. But this is very consistent with what we know about heat transfer. Now let's say you don't want to do a contour, but you want to draw the velocity field. So we can do a vector for that. We can do locations plane 1. We want equally spaced. Let's say we want 1,000. Variable, we can do velocity, color. It's super distracting when the vectors are colored by speed. So let's just click through the black. Let's apply some constant color there. Now let's reduce the symbol size. There we go. So as you can see, it's relatively consistent. Let's get a better view by clicking ISO. Yeah, everything is consistent. It goes from right to left as we would expect. But if we want more resolution, we could do, say, 100,000 vectors. It'll take a while to render, but we should get more resolution. There we go. Isn't that a pretty picture? Now notice the velocity near the wall is much slower, and that's because there's wall friction. Speaking of wall friction, the last thing I want you guys to do is go to calculators, go to the function calculator. With this you can calculate many things. So let's say if we want the total amount of force on that wire as a result of the fluid friction. So location heated wire, direction global, all fluids. The force is very small because we're only going at 10 meters a second. Now if say we were doing a supersonic rocket simulation, we would have this be much higher. We can also find the force on the outer wall in this fashion, and that's a little it's about 100 times bigger due to the much greater surface area. Now that's, I believe, all I wanted to show you guys for this fluid simulation. Mainly just the process of how to set it up and run it. So that will be all for today. Have a great rest of your week, and good luck with all your tests, quizzes, homeworks, and presentations, or whatever else you got in your classes. See you later.